So in this module, we're now going to look at crystallographic directions in hexagonal systems. And we do this because there are some complications when it comes to hexagonal. But let's first start with directions in the other systems. So what we find is that certain directions certain directions in a system share common features. So if we're talking about a cubic system, the features, for example, in the 1, 0, 0 direction, this direction, so basically the y-axis, the direction in the x-axis, the y-axis, which is 0, 1, 0, or the z-axis, or any of these others that kind of run along the edges of a cube, share the same properties, the same pattern of atoms and the same properties, electronic, mechanical, and so forth. And so it doesn't really matter for the crystal, for example, whether you're talking about the 100 or the 010. So what we term these is crystallographically equivalent directions. So they share a common arrangement along a given direction and have a common spacing of those atoms. And so these are known as families of directions. And so we give them the triangular brackets to denote this is a family of directions. So again, for cubic, basically all of these directions that you see down here, so the 100 type, so there's negatives, there's all the different directions of that, because again, we can kind of rotate that cube and it has the same properties whether it's the x, y, or z axis. So that's why we call them equivalent, and that's why we think of them as the family. But the important thing to note here is that if you look at one of these, you can see that it's a combination of 1 and zeros, right? One's 1 and then 2 zeros in some combination, and there might be a negative, right? However, when we get to hexagonal, we have this interesting system where we have different axes down here. So let's look at the different axes that we have. So this is known as the A1, A2, and we usually call this the A3 axis actually. And so let's look at these different directions. And so if you look on the crystal up here, these are the same, they're equivalent, right? The packing and the spacing between atoms is the same in these three types of directions. However, if you look at the crystallographic directions, the indices, you have 100, you have 010. Okay, so far so good. But then you have this other one where it's described as bar 1, bar 1, 0. Right? So it's no longer that we have permutations like we did in cubic, right? All these are just permutations of the same 1 and zeros. Here, though, this now kind of defeats that, right? So we don't like this as, people who study crystals, because we want to be able to look at the direction and say that they're going to have similar structures because they're permutations. So we would like this to be a permutation, all of these to be permutations of one another. So that's where the complication comes in. And so we can't do that when we have X, Y, and Z, or three axes, A1, A2, and Z in this case. So what we have to do is we actually have to define a fourth indice so that we can get permutations. And so now instead of just A1, A2, and Z, we have A1, A2, A3, and Z. So for those of you that know about coordinate systems, you'll know that you don't need three axes in a single plane, right? It's over defined. So bear that in mind, that we're over defining the system to solve this problem so that all of these look like permutations, right? So that's the goal. We want all the directions to look alike, to be in the same family of directions. So to do this, we're going to have to convert from the 3 index to this new 4 index system. And so this is what you'll see in a large number of the hexagonal things that you read. You'll see 4 index. Every once in a while you might see 3, but 4 is much more common when we're talking about hexagonal. And all we need is just to, we don't have to derive these equations for ourselves. These are given to you here in the slide, but also in your textbook. You can find the conversion from the 3 index, where we define the indices as capital U, V, and W, and then the 4 index, where we lowercase u, v, and now at lowercase t along with the lowercase w. So these are the conversions to do that. And so we had a procedure for determining the directions in other systems, and so I'm going to sort of show you the new way to do this in hexagonal. And I caution you from venturing off into different directions here, because it is next to impossible to do this directly in 4 index notation. So if you're going to use these procedure steps, don't sort of deviate from them. And so here they are. So number 1, we're going to follow the same procedure we did to find the indices in 3 index notation, right? So A, A1, A2, and Z. So we're going to treat it just like we did before. However, now, once we have those indices, we're going to convert. So we're going to use those equations here in this previous slide. We're going to use those to go from the 3 index, which we just found, and to 4 index. So again, do not try to do this procedure directly in 4 index. You'll get some strange answers. So make sure you do it in 3 index and then convert. Again, I've tried this many times and it just is very difficult to get anything useful. So make sure you do it in 3 index and then convert to 4. And then you're going to follow the same procedure. You want to adjust so you have the smallest integer values, just like we did before. And then you're going to put it in square brackets. And in here, in this case, we're going to have UVTW, so it's going to be in 4 index. And so this way, you'll be able to see it's a direction because of the square brackets, and you'll be able to tell it's hexagonal or one of the other systems that uses 4 index notation. All right, so let's go through an example. So we've got this direction here that I'm showing you in the slides. Let's go through and kind of work that one as a quick example before I have you go off and do your own. So, all right, so we're going to follow the same procedures that we did to get 3 index. So like always, I like to make a table. Here, I'm going to label it the same as what we have on the screen here. So A1, A2, and Z, just so we're consistent with that. So again, you find your projections. And so in this case, if I want to get to this point up here, what I have to do is I have to follow the projections. So in this case, it's projected 1 length. You can kind of see it. It's basically up here. So we can get that by going 1 length of the A1 axis. So that's 1A. And then from there, along the A2 axis, you can see that's running back into the screen. You also go 1 length here. So that's 1B. And then you go 1 unit up to this to get to this point. So I'm basically just going from the beginning point to the end point to find my projections. And so that's also 1C. Okay. So if I wanted to define this in 3 index notation, it's 1, 1, 1. That's our point, right? But again, similar other directions are not going to have the same permutations, and so we want to convert. So I'm going to use those equations that I had in the previous slides, and I'm going to plug in my values, which these are UVW, the capital version that you see here. So if I plug those in, so those were all 1s. So I've got a 1 here, a 1 here, 1 here, and 1 here. So these basically end up being the same, but they're flipped. And then the T, if we go back, the T is the combination of both, minus the combination of U and V. And so that is these new ones. The new ones are the lowercase. So I basically take the combination of these two values and take the negative, so that's negative 2/3. And then W is the same as W. So basically, if you think about it, we're not really altering the z direction. It's all in plane, which is getting thrown off. So W is equal to a capital W. All right, so we've got those. And so at this point, we've converted. And our next step is we take these new indices that we have, and again, we have a lot of thirds that we see, and so we're going to adjust to get the smallest integer. And so as you probably imagine, that's multiplying by 3. So if I multiply by 3, that gives me 1, 1, -2, and 3. So now I put it into direction form, square brackets, and then the bar over top for negatives. So that gives me 1, 1, bar 2, 3 as my direction. So this is the direction over here in 4-index notation. So again, if you try to do this directly like we have before, but in the 4-index notation, you'll get something different, and it's really because of the complication with this new axis. So again, start with 3, convert into 4, and that will give you the answers every time.